Hey guys, we're going to go ahead and work on chapter 11.6, which is ANOVA. So let me go ahead and get all this started. Hold on, let me get it to come up. Okay. Alright, here we go. So, ANOVA is analysis of variance. And basically what it is when you have more than two means and you want to see if they're all the same in value or statistical significance. So, so let's talk about this. So what we're doing basically is we're comparing more than two population means using an ANOVA test. And ANOVA is analysis of variance. Okay, so there's only one null and one alternative hypothesis for ANOVA, which makes it really easy. The null and alternative hypothesis is to compare the means of three or more populations as follows. So the null hypothesis will be the mean 1 equals mean 2 equals ... out to the mean k, which is, you can go up I think to 20 different means for ANOVA test. Your alternative is at least one mean differs from the other. It only takes one to reject that null, because in the null you're just saying they're all equal to each other. So if I'm comparing like three populations of students, maybe the campuses of Cartersville, Rome, and Marietta, and I'm studying like the mean GPA, all I have to do is find one difference. If there could be a difference between Cartersville and Rome, as long as I have one, then I'm going to reject that null and keep my alternative. Okay, so rejection rules for ANOVA. We're going to say we're going to reject the null. Is F is greater than or equal to F significant, or alpha as we call it, so the critical level of F. Alright, so let's do an example. So medical researchers studying the effect of vitamin C on the common cold grouped study participants into three groups. Group 1 took 1,000 milligrams, Group 2 took 500 milligrams, and Group 3 took no milligrams. Hint, remember when you're looking at Group 3, 0 is still a valid mean because they didn't take anything. The participants were observed for the year, during which time the number of colds that each participant has suffered was recorded. Using the data, the researchers performed an ANOVA test, which resulted in the following ANOVA table. Okay. All right. So this is the ANOVA test. We don't have to. The ones when you do it in Hawks, you're going to have to use the table to figure out how to do these. So I didn't go through everything step by step because it's kind of difficult. But if you want the actual table itself, if you go to page 769 in the book, so let's quickly go over it. Okay, so we're missing some values in this table. We're missing sum of squares treatments. For the sum of squared errors, we get 49.203. The sum of squares total is 52.0606. For the treatment degrees of freedom, there's 2. Why is there 2? Well, because we had 3 categories. Remember, people who took 1,000 milligrams, people who took 500 milligrams, and people who took no milligrams. So, so 3 minus 1 gives you 2. Okay, we don't have the degrees freedom of error, but we do have the degrees freedom total. We do have the, we do have the mean squared treatment, but we don't have the mean squared errors. And finally, we don't have the F value, but we have our P value and our F critical value. All right, so let's start filling in the table. So for the sum of squares treatment, the easiest way to do that, if we're going up and down, all we have to do is subtract 52.0606, subtract 49.203, and you get 2.857. So that would go here. Degrees of freedom error, it's going to be 32 minus 2 gives you 30. Okay? So for mean sum of squares, or mean square for the errors, what you're going to do is you're going to take 49.203, which is your sum of squared errors, divided by your degree of freedom errors, which we figured out was 30. And then for that, you're going to get 1.6401. Okay, so let's keep going. All right, so we did that. Now, to get the final F value in the table, we do 1.4288 divided by 1.6401. And you see up there in pink, that's where we solve that, and you get 0.8712. Okay, so what can we find? All right, so first let's state our alternatives and null hypothesis. Null is always going to be the mean of 1 equals the mean of 2 equals the mean of 3. Alternative, at least one is different. So we have a level of significance at 0.05. Thus our alpha is 0.05. So we can draw our conclusion from the ANOVA test by using the p-values as we have in the previous section. Note that the ANOVA table states that the p-value is 0.4288. Since 0.4288 is greater than 0.05, we have a p-value greater than alpha, so we fail to reject our null. So what does that mean? If you fail to reject your null, then there's no significant evidence at the 0.05 level of significance to support the researcher's claims that there's a significant difference between the mean number of calls suffered per year for patients who take 1,000 milligrams of vitamin C and patients who took 500 milligrams of vitamin C and patients who took no vitamin C. So what are we saying? We're saying there's no difference in that. You could take 1,000, you could take 500, you could take no, and you're still going to have the same number of calls. Okay? Okay, remember that rejecting the null hypothesis in the ANOVA test supports the claim that at least one of the populations is different from the others, but it doesn't indicate which one is different or by how much. This test only shows that there's a difference. For you to find the difference in the means, you have to go back to chapter 11.1, 11.2, which we didn't cover. So for this class only, we're going to say, okay, there was a difference in the means or there wasn't a difference in the means. Okay, so let's look at this one. Researchers at a drug company wish to test whether their drug is the best on the market for lowering cholesterol levels for middle-aged women. To compare the drug with other drugs on the market, 30 women with high cholesterol volunteered to take part in a 6-month study. The women are divided into 3 groups, and each group is given a different cholesterol-lowering drug, one of which is the drug made by a company. The women's cholesterol levels are measured at the beginning of the study and again at 6 months. The difference between the before treatment and the after treatment cholesterol levels for each woman is recorded in the following table. Note that each study participant experienced a decrease in cholesterol levels over the 6-month period. Okay, this is important. You guys are going to see this, my nursing students especially, and psychology. You're looking at what happened before something was done and after. And what we do is we look to see the difference. We don't look to see the actual beginning number and end number. We find that difference, and that's what that's saying. Using the data to perform an ANOVA test with a 0.1 level of significance, assume that the 3 population distributions are all approximately normal with equal population variances. What conclusion can you draw from the ANOVA test? Okay, first you can use Microsoft Excel, and then we're going to use the calculator. Okay, so here is the difference. So as we see, drug 1 lowered the first lady 18, the second lady 19. So we're talking about, it's a measurement of your cholesterol. So, I'm sorry, milligrams over, is it deciliters? I don't know. Sorry about that, guys. But it shows what it decreased it. So if you look at that, you'll see everybody decreased, but we want to see which did they all decrease the same amount. So, okay, so you enter your data in Microsoft Excel. I'm going to show you how to do it in the calculator, but I just want to show you how they give you the table. It's really pretty in Excel. So you fill out, you put your stuff in, and then you go to the ANOVA test. And look, if you look down here at the bottom, look at that ANOVA table. So it gives you the sum of squares treatments, sum of squares errors, and then the total. Degrees of freedom within the group. And instead of, you see between groups and within groups, the between groups is the treatment, and the within groups is just your error, because it's measuring for errors that can occur within the groups themselves. Okay, you see that F value, you see that F critical, and you see that P value. All right, so, excuse me, because our P value is 0.0744, which is less than our level of significance, 0.10, we reject the null. So that means there's at least one population mean that's different. So we can't say which one it is, but we can say there's a difference. So let's play with it. Excuse me. But what you can see though, and if you look at and you can look at the data, but you have to be really careful of making assumptions. Okay, this is where 11.2 and 11.3, where you're doing a 2 mean t-test and a 2 mean v-test. You can't do it. You can't make assumptions without doing this. But if you look at the descriptive statistics, you can see drug 1 and 3 lowered the levels by 2.01, and drug 2 lowered it by 18.2. So you're thinking maybe drug 2 is different, but remember, you got to be careful making those assumptions, especially when your sample size is different. Okay, so to do the TI-83, so go to the ANOVA test by entering the sample data. So the first group would go in L1, second one in L2, third in L3. Press Stats, scroll to Test, and choose H, which is ANOVA. Okay, so you'll need to enter this list that contains the sample data in your ANOVA test. In the case we entered ANOVA, L1, L2, L3. Press Enter, and this will show your result. So if you look here, you're still seeing your factor, which is another word to say treatment, and your errors. Okay, and you get the p-value, which is 0.0744. Again, that's less than your level of significance, which is 0.10. You reject the null, and again, it shows that there's at least one difference. So play with this. You'll have to use filling in the tables on Hawks, and you'll actually have to answer some questions. It's really not that bad if you use your calculator. And let me know